everyone. Good afternoon, depending on your time zone. Thank you for taking the time to join us for our webinar, Accelerating Aerospace System Design. My name is Jocelyn Pazlowski, Modelon's Marketing Director, and I am the moderator of today's webinar. This morning, we will begin with an introduction to Modelon and an overview of how Modelon Impact was designed to accommodate the aerospace sector. This will be presented by Michael Seeleman, Modelon's Aerospace Industry Director. Following Michael, Clement Koick, Modelon's Aerospace Senior Simulation Engineer, will cover an overview of dynamic versus steady state simulation, multi-point design, and will conclude with a demonstration of how a model can be deployed into a custom web app. Today's presentation will last roughly 30 minutes. We will have about 10 to 15 minutes available for Q&A at the conclusion of the presentation. The Q&A button is at the bottom of your screen, so please feel free to submit your questions during or after the presentation. A link to view the webinar on demand will be available and emailed in the coming days. So if there are no other questions, I'll go ahead and turn the mic over to Michael.
Thank you, Jocelyn, for that introduction. I want to say that I'm really excited to talk to you about what we achieved. And I should say that I do get carried away occasionally when I'm excited. But today I will not dive into the technical details, but give you a high-level summary of what we do and have been doing. If any of you is interested in the nitty-gritty, do let me know. I'll be more than happy to follow up with any additional details. Now, I want to start by introducing Modelon. Over the past 15 years, we've grown to be a global company with offices all around the world. We are headquartered in Lund, Sweden, but we have also established offices in India, in Japan, in Germany, and in the US. Now, our portfolio of customers includes, I would say, a lot of large global enterprises representing the aerospace industry, but also automotive, energy and power, and industrial equipment. Our company has been built and developed on the promise of delivering open standards technologies using Modelica and the functional mockup interface standards. And we now have a portfolio of 17 Modelica-based libraries that are integrated directly into our cloud platform, as well as deployed to cover any physical domain. Along with our growing portfolio, we also have a growing team. It's an incredible team of approximately 100 who believe in open standards and are committed to making system simulation accessible to everyone. Some are brilliant thought leaders in their field. For example, Clement Koick, who we will be hearing later, who has extensive experience modeling aircraft vehicle subsystems. So let me jump specifically into the aerospace context. Despite the current downturn in travel, we really live in a connected world. Transportation, be it by car, train, or aircraft, is a key part of this. However, there is a price. We see this in the daily news, and reducing emissions to a sustainable level is really a key societal need. And we at Modelon think that technology is a key part of the solution. Our technologies have been built on years of experience. We've learned what's needed to reduce emissions while maintaining performance. Modelon is proud to be bridging the gap between public interest and private industry to lead and advance this research. The key used to be component technology alone, but today this alone is nothing. Systems design and integration are the enablers for better technology because we ask how to get value out of so many new technology options to choose from. We at Modelon believe that systems design and integration need open standards. We believe that an entire system is only as good as the sum of its parts. Modelon Impact in aerospace covers vehicle subsystems, including thermal management with environmental control systems and vapor cycles for supplemental cooling. It covers actuation, be it hydraulic or electromechanical. It also covers secondary power with a trio of electrical, hydraulic, and pneumatic power. The fuel system, ranging from fuel management to thermal analyses. And the landing gear with its kinematics, the wheels, tires, bogies, dampers, and so on. Modelon Impact in aerospace also covers the propulsion, be it conventional or hybrid electric, for instance. And it also covers the aircraft level to predict aircraft dynamics or flight performance in technology assessment. These subsystem models have been developed and grouped exclusively to serve the needs of the market. And these libraries are part of Modelon Library Suite and are built into Modelon Impact. Together, they cover all facets of aerospace, ranging from basic components to system architectures and application examples. With our industry experience and commercial libraries, we're proud to introduce Modelon Impact as the key enabler for aerospace systems engineering. When we set out to develop our new platform, we recognized the gaps in the physical modeling toolchain. So the separation between tools for dynamic simulation and tools for steady state simulation, and also the integration of workflows. Within Modelon Impact, we then use object orientation to make large-scale modeling efficient. As you can see here, we start with predefined templates. And if we take layers of these, we define our model architecture. And within these templates, we have placeholders. And when we're populating these placeholders with specific modeling assumptions and parameterization, we create architecture configurations. And based on all that, finally, we assemble the use cases based on what we want to achieve on a given day in the design process. And all the time, we can customize the basic component models or the templates, and also the workflows using Modelica, Python, and all the powerful APIs in the background. Collaboration is a key part of everyone's daily job, I would claim. And I think that those of us understanding a component or a system really inside out, they're probably often asked to explain some intricate aspect to some decision maker, another engineering group, or maybe even the sales department. And I think that we all want to share our insights, but some of us often get frustrated with the simplistic tools that are available to share these insights. Now, with Modelon Impact, you can give your stakeholders access to the real thing. You can quickly build simplified views of complex models. And you will see soon an example of this in the demo by my colleague Clément. He has this web app for the actuator sizing and analysis. But the possibilities, they really go much beyond this. You can, for instance, also share your model and also all the data, the views, plots, experiments, and more, just by sending the hyperlink to your model workspace to a colleague. Modelon Impact also allows you to work with a range of simulation problems, which often required completely different tools in the past. So let me tell you a bit about this. Modelica, that's the modeling language we use, has originally been developed for dynamic simulation, and this is therefore the key simulation problem for all Modelica tools. And this is also built in from the start into Modelon Impact and leveraged in the vast library suite we deliver. Then steady state problems were usually solved in specialized tools, often in-house developments. But Modelica always included all mathematical tools to pose these steady state problems, but the practical tool functionality only cared about the dynamic simulation, really. Now, I recognized this several years ago and started to fill this gap with early adopters. And I even wrote a blog about this in 2015 that you can look up if you're interested. Now, this year, we finally released the full functionality and the engineering workflows. And the key methodology here is the physics-based solving, which allows us to use and solve large-scale steady-state problems and solve them in a robust and efficient manner. And this is available now in select libraries, and we're gradually rolling this out to more. And the fact that we have built this into Modelon Impact, I would claim, shows what benefits Modelon can bring to the industry. We listen and we provide broad perspective. Now, in his demo, Clément will show and describe this live, but as the differences here between steady state and dynamic are subtle but critical for engineering success, let's recap this here quickly too. So a dynamic simulation predicts how an engineering system behaves over time, for instance, this aircraft. If a pilot changes any actuator on the aircraft, then over time, the position and orientation change. The result is then the entire trajectory of all the variables over time. Now, if we're interested in some equilibrium condition, then we actually may have to simulate a long period before reaching this equilibrium condition. With steady state, there is no notion of time. We just specify the operating conditions and directly solve the system. If you look at the image here to the right, you see that for a given case, the aircraft is simply at the equilibrium. And we can, of course, also change this by going to another operating condition, maybe at a higher speed, and find that a lower angle of attack is required to provide the necessary lift. Now, the advantages of genuine steady-state simulations include speed. They're several orders of magnitude faster. The results are also easier to post-process because they only contain the points of interest. And they additionally facilitate batch simulations when you're implementing your engineering workflows. But I'd say so much about the theory. Clément, do we want to show what this looks like in reality?
Yeah, let's try to do that. I will try to share my screen. I need to grab the correct one. Okay, I hope you can see my screen now. Can you confirm, Michel?
Yes.
Good. So I hope everyone can see it and that you won't be blocked with my face. It's not that a nice experience. I want to start this presentation by first introducing you to Modelon Impact user interface. So I will be really quick because we already had a webinar on the topic, but I just want to make sure that you are all aware that it's a web browser interface. That's why I'm here on Google Chrome. And we have the canvas in the middle, and we have left and right panels. On the left one, you will see the workspace where you have all your models that you can edit, build a new one. You have the favorites if you have some, and you have the libraries here that are built in Modelon Impact, and there is, in addition, also Modelica standard library, which is really useful. I only show here the one from Aerospace, but you see we have also more that I just turn on and off by just clicking on the checkbox. We have three main simulation mode here on the top. So this is the modeling mode. Here we have the experiment mode where we can change parameters, change case setup, and experiment on the model. And here we have the result where basically we study the result, the analysis, and the, sorry, I should have opened that, but the right panel is changing based on the mode you are on, just to display the relevant information. So here we can parameterize the model, for example. Great. So I will try to cover in this short demo 3 main topics. The first one is to introduce you again to steady state and dynamic simulation by showing examples. And I will also present the sizing scenarios of the spring here on the mass spring damper system. So this is really to highlight that there is this on and off design simulation modes. In on design, you size the system. In off design, you study the behavior of a sized system. On a second time, I will show how we use custom functions in Modelon Impact to automate our workflows. So you avoid performing manually lots of actions. You actually rely on Python scripts that do the action for you. And in the last part, I will present the actuator design web application on which we will size an actuator, a hydraulic actuator, based on a mission profile. And this is available through a nice, simple interface, which is a really good way to spread the model to a broader audience without letting them make all the change you don't want on your model, just performing a set of action on it. Great, so let's start with this steady state versus dynamic example here. It's a simple mass, which is submitted to gravity force. Acceleration force. And here we have a spring damper that will compensate the weight of the mass. So on this example, let me close that here. I can easily move it and zoom if I want. I will start by simulating the dynamic behavior of this model. So if I click on simulate, it directly simulates the model here. It was already compiled. So now I'm presenting on Zoom. I experience a bit of slowdown in this refreshment here, but it's usually quite fast. And we can say that we have a set of results, which is the dynamic simulation we did here. We have some embedded views in this model that allow us to plot the mass position. So I can just grab the position and see how it behaves. I could also navigate here through the tree and grab some other values if I want. I can, for example, take the spring constants of this, the stiffness of this spring, and you see that it's 2 kilonewton per meter. Great. Then we will actually go back to this mode and just say that we want to actually enable this physics-based solving, which is the insight of the engineer that we put in this code. So we make sure that the steady state simulation happens in a robust way. And we also have the possibility to do sizing on this model. But for now, we let that the way it is, so unchecked. We won't size, we will just study the behavior, so the off design simulation. And now we can run the steady state simulation. This requires recompilation. It's not the same set of equations that for dynamics. And once the model is compiled, sorry, we directly simulate it and we can observe the results. So simulation has finished. I think it's also taking a bit of time to refresh apparently, but we should get it coming. I'm on a cluster in the US, so maybe also the fact that I'm in a small village in Germany might be a problem for connecting with it, but it's actually working. So here we have simulated the steady state mode, and we see that directly the result of the position of the mass is the endpoint of the dynamic simulation. So we don't have to simulate all the transient, and maybe we don't need to find the endpoint. And here, the notion of time, for example, is actually not something we really need. If I remove from here the dynamic simulation, then you see the axis time disappears because it was just there for the dynamic mode. It's not really needed to represent a steady state point. Great, I've introduced steady state and dynamic. Now let's present the sizing case. So sizing, in this case, I selected this scenario. I want to answer the question, what should be the spring stiffness so that the mass equilibrium point would be, in this case, 0.7 meter. So located here. And I don't need to recompile this model because I use the same FMU. The compiler has made the FMU in such a way that the solver can hide the set of equations that it does not need and enable the other ones to solve this second problem. So we have one FMU, we can solve two problems, the sizing one on design and the behavior of design. And you see here, obviously, we have specified this 0.7 meter, so we get this value. And the spring was computed here, and we get 1.3 kilonewton. If you remember before, I said it was 2 kilonewtons, so it makes sense. We need a lower stiffness for the mass to be at a lower point of equilibrium. Great, so really simple example, but I wanted to show already quite some capabilities with that. So the simple example is here to make it a bit more easy to understand. We actually implemented all that in the jet propulsion library, which is way more complex than just a spring mass example. And here I selected an example, which is a geared turbofan. It's the type of jet engine that you can find in an Airbus A320neo, for example, or a Boeing 737 MAX. And basically, you see here we have the core flow going here, through here, and here we have the bypass flow. So the air coming from the left. And you see that we have a reduction stage here that enable having a different speed on the rotation of the fan with regard to the turbine. So that enables us having better efficiency actually on this engine. Good. So in this model, we have actually already some views already built in also. And the physics-based solving is also built in the library. So we have the case setup here, a set of views that enable us just looking at the typical parameter we could change just to change the simulation case. So we will start by doing the physics-based solving simulation on design, so sizing case. And if you look at these views on design, there is a bit of lots of parameters that will be sized during this simulation, so I will not show them all. But for example, you see that the throat area is not sized for the nozzle, and that is one of the things we will size among all others. Great. So if we go to the custom functions here, simulate single point, this custom function is really tuned to fit the jet propulsion library. And if we go on the experimentation mode, we can see here that we will size this design point and we can give it a name. So I gave it top of climb, which is actually the design point here. For this jet engine, I can simulate this point. And in the meantime, I will just grab my documentation because I wrote a small piece of documentation just to have all my text here to make sure that I don't forget anything. Great, so here we have simulated the top of climb. You see it here. And if we look at the on-design simulation, we click on the result, you see that we have sized the throat area of the nozzle that I commented before. Great, so what we want to do now is to simulate actually the off-design scenario. And for that, we actually want to reuse the on-design result because we have sized the system. So now we want to study the behavior of this system, not another one. So we have a dedicated also custom function. The simulate single point is doing that also, but we also have another one that is performing steps. When the 2 points you simulate are too far away and you want to make sure that you will converge, then this function will actually split this big step into several smaller steps. So instead of converging directly from the design point to the off-design point, we will converge from on-design to off-design smaller steps until reaching the objective here. So we will use this second function, which is the A2 simulate with stepping. So we see that we take the design from the top of client, it's the one we named it, and we will make smaller increments to reach the value, which is the takeoff in our case, which is at sea level, and the specification said that there is a delta temperature with regard to either, which is 15 Kelvin, and we have a Mach number of 0.25. Great. So we see here we have built a different experiment. We have modified the parameters of the original model, and we can simulate this example. We don't need to compile anymore, because as before, we hide the set of equations which are no more relevant. Simulating is finished now, and we can look at the off-design results, which are appearing here. And we have on the takeoff, for example. And here you see all this appearing here. So it was showing slowly, but actually, if I look at the simulation log, you see that it took, well, 34 milliseconds to solve this this problem. So it's really fast. It's just I experience some trouble currently, and I apologize a bit for that. Good. So you have already seen some nice thing we can do with custom functions. The next thing I want to show you with custom function is actually what we call multi-point design, which is when you want actually not to size only based on one single point, but based on one single point plus making sure that you meet the constraints for the off-design points. So here you see we have the top of client, which is our design point. And for the other one, we have cruise scenario, rolling takeoff, sea level static, and these one are off-design points. So what we do with this methodology is actually to graphically connect this model to make sure that we size this system meeting the requirement on the off-design points here. So this is quite a complex topic. We have a video on YouTube if you're interested. I think we can join it to the follow-up mail to this webinar. But Michel explains really well inside what is this methodology and how far you can get results with it. And yeah, there are different variants, so he really presents that really well. So I won't comment much more on the methodology itself. What I want to say is actually that this is performed with this custom function, which is generate multi-point. And this custom function actually grab the model that I presented just before and build this model almost entirely for you. So you have really an automation that enables you to write a new model, to write Modelica code, to write equations in the code layer, and to add it to the workspace. So it's really powerful. It's just to give you an idea of what we can achieve. And this model, I actually simulated before, just for sake of time, but you see it takes 0.6 seconds to simulate. So it's really fast to converge also in a robust way. So here we have had a quite view of what is possible with custom function. I will move to the last topic, which is the actuator sizing and behavior studying. So here we have a hydraulic actuator, which is a hydraulic cylinder and a control valve. It's a really simple model here. It is regulated in position. So we have a sensor that is attended to the controller. And based on the input you command and this controller, we will actually move the valve so that the power coming from the pressure source, the hydraulic power will be actually metered into the two chambers of the hydraulic cylinder. So we make sure that we can reach a given position facing a given load. So what I want to do here is to go to the actuator web application. And this is a new tab, you see, that is actually connected to the model. And here what we will do is to take a mission profile, which is a set of forces versus speed points. And based on this scatter data here file, we will size our system. So here I have few points, maybe 30, something like that. But in the real engineering workflow, you might have thousands and like many thousands. So the first thing that we want to do here is to apply a level of engineering, which is to actually remove the points that are not sizing for sure. So you see this one, for example, requires less speed than this one for the same amount of force, so we can remove it. And basically when I click on fit here, this is what happens. There is this type of logic applied that we put in this scripting. So we actually keep only the points that are relevant for us. Then for the sizing, we need to provide the boundary conditions, those are pressures, the fluid density, and also a criteria, which might be, in this case, it's my choice, I selected that, the maximum safety speed, which is the speed we don't want to exceed in order not to, for example, burn the ceiling of the actuator or to have not too much kinetic energy when we have a failure. If we have to reach the end stop, then we don't want to exceed this speed. By default, it's set from the model. So we have predefined values here, and we can click on optimize, which will size the cylinder area and the cylinder valve, flow area of the valves. So we make sure that we have a characteristic here in green of the actuator, which is above all points, but below the maximum safety speed here on the left. Great, so we have the maximum safety speed of 0.1. We can make just a variant, which is 95 millimeters per second, for example, just to show that we will get another equilibrium point. Here you see 21 centimeters square. And before, I think it was 20.5. So we obviously, if we reduce the maximum speed, then we have to move the curve to the right. So we make sure that all points are within, are below the green curve. So that makes sense that basically if we reduce the speed, we increase the area of the cylinder here. And once the area is sized, then, well, we have decided on this web application to make a linear analysis where we study the frequency and a response of this actuator. But what is important here is really to say that this is a web application that you have to tune for your need. It could be totally a different topic. You might not be interested in hydraulics, but really we can do lots of different studies on a single model connected to Modelon Impact through a web application. And if you scale that to a usage, then actually you can give external people accessibility to the usage of your model without having the possibility to really modify the model. So it's really powerful for spreading a model to a broader audience. So I have done my three parts here on the presentation. So I will just stop presenting and give back the ball to Jocelyn. Hopefully we have nice questions to answer.
Great. Thank you, Clement. Thank you, Michael. We will now move to the Q&A section portion of the webinar. We will try to address all the questions we received, but if we run out of time and do not get to yours, we'll contact you directly to close that loop. So also, if you have questions that you want to address directly with Michael and Clement, their email addresses are on the screen. So please feel free to reach out to them directly. Okay, so the first question is in regards to the multi-point design approach and designing a component for multiple operating conditions. Is this restricted to the jet propulsion library?
So that was on my part, so I take it unless you want to jump in, Michael, but the multi-point methodology is not restricted to jet engine. You actually on the actuator web app, what we did is kind of a multi-point design because we had several points and we optimized so that the curve is above all these points. So no, it's not restricted, but the custom function I showed were specifically made for the jet propulsion library. So if you have another use case, then you might need to make a variance of these custom functions, but the approach is perfectly something you can scale to other systems.
The next question is, I have my own Modelica libraries. How difficult will it be to import them?
I can take that one. All right. So it's straightforward. There are ways in the graphical interface for you to upload, for instance, a zip file with all the Modelica code. That's just one of the ways to interact with the graphical interface. I want to attach a footnote. Obviously, the code has to be correct in the Modelica language, and our computer science colleagues, they say it's got to be compliant with the language specification. And yeah, for all the migrations that we've supported, often it's been useful to activate this pedantic mode if you're exporting from another tool. And yeah, with that, we've been able to support this kind of imports in the past.
The next question is, do I need a full Modelon Impact license to use a web app?
So I take the question, but actually it's more something like for business developers to answer. But I'll give the tech answer. We have 3 different licenses. So we have Modelon Impact Base, which is the software without the libraries. We have Impact Pro, which includes all the libraries. And then we have one for runtime, which enables you to just run the web application in this case, or an FMU in general. So it would be the minimum you need, but I just think there are many variants, and the best is always to tell us what you want to achieve, and maybe we find a better way for you to do that. For example, if you want to spread a model like that, like with the web application, if you host it on your server, then the person that wants to access this web application does not need this license. So it might be convenient for you, for example, to be able to spread a model using your own licenses instead of making your customer having licenses also.
Great. Next question is, if you build a model for a gas turbine, could you generate C code for integration with an aircraft model not using Modelon?
I could take that, unless you, Clément, want to. Yeah, so yes, definitely. It's definitely possible. We're exporting C code, and there is also an additional standard that you can use for the exported C code. There are actually different variants. This is the functional mockup interface, which is a standard to exchange models when they're essentially complete. You can still change the parameterization, but if you want to exchange the models or run co-simulations, this functional mockup interface standard helps you a lot to do the interfacing. And there are 2 flavors that might be interesting here. You can ship literally the C code within the functional mockup unit, or you can ship binary code. In some cases, you still want to obfuscate the code in one way or another. So shipping binary code for Linux or Windows is also supported by that. We'd be happy to follow up if you're interested in some more of the technicalities there.
Thanks, Michael. The next question is, would I be able to see the code layer in the libraries, and would I be able to build or extend that, basically create my own technology model?
Yeah, I can also take that one. So yes, you can access the code layer. I think that's one of the main parts of our value proposition. We talk a lot about facilitating the reuse. So part of what we're offering is making very transparent. You can see nearly everything in the Modelica code and the libraries that we're offering. So we're making transparent how we do it. And then there is this object-oriented principle to the Modelica modeling language, which gives you a very efficient way to adapt the implementations we have and the hooks to drop in your custom or proprietary functionality. A lot of our users, they take the bulk of the content from us and then add this content on top of it using these hooks and object-oriented interfaces for their tire data or heat transfer correlations, pressure drops, etc. So yes, definitely possible.
Maybe now I have it open. I can just quickly share my screen, but I can just show it. It's really fast. If you can see my screen, we have view source code here, and then you would have a pop-up window with the code, and it's read-only because it's a library, which is encrypted in the sense of you cannot modify it. But if you duplicate, for example, the model to your workspace, then you can, instead of view source, edit the code source yourself. I don't know why it's taking time, but it is. And it's actually an option that you can activate here, enable code editor. So if I go here again, I can edit the source code now instead of and typing whatever the comments, and you can save it. Good. So it's possible.
Great, thanks, Clement. We have just a few more minutes left. I'm not sure that we're going to get to all of the questions listed. So again, we will follow up if we are unable to get to your question. Then the next question is in regards to the web application. Is that steady state, and can I use the same base model for dynamic optimization and steady state sizing?
So the web application for the sizing, the way I designed it with my colleagues, we decided to make it steady state. It could have been dynamic, but for the sizing, it's steady state. But the second part is dynamic because it's a frequency response, and it's the same model that can do the same thing. But you need recompilation because it's a different set of equations for steady state and dynamic, and a different solver. So I hope I answered the question entirely.
Okay, the next question is, how can I create my own web apps? I have an idea, but how do I do it?
Yeah, I can maybe take that. So, I mean, generally, there are probably two main options. You can take one of the web apps that we ship with the platform as a template and adapt from there. If there's a variant that's close to what you want to achieve, that might be easier. The other option is to build it from scratch. With the web apps, where the name tells it already, we're using web technology. So there is HTML, JavaScript in it, and one key ingredient, the so-called REST API, which is a very easy and powerful API to query certain tasks or results from the Modelon Impact platform. So you can, for instance, run a simulation with these parameters, change a model, get an image from the model diagram, and things like that. And through those building blocks, yeah, you can go forward and implement these.
Okay, so I think we have time for one more question. I think this one will go to Clement. The Bode diagram is done with Modelica model, or is that a Python package?
Yeah, okay. I'm reading the question at the same time, sorry. So the Bode diagram, the Bode diagram itself is plotted with a Python module. It's Plotlib, matplotlib, sorry. But what is plotted is results from the simulation of the Modelica model. So yeah, that would be the answer. The graph itself is just calling a Python module, but the points that are plotted are simulation results from the Modelica model.
Okay, great. Well, we've reached our time limit for today. Again, like I said, we will follow up with on the questions that we did not have time to answer. So Thank you for your time. And if you do have questions, again, please feel free to reach out to Michael Clement or myself directly, and we will put you in contact with the right person. So that concludes today's webinar. So thank you for your time. Have a great day.
Thank you.
Bye-bye.
Thank you.
Bye.